Welcome everybody to the OxTS webinar, Introduction to OxTS Inertial Navigation Systems. This will be done by my colleague Caroline Oakes. There'll be time for questions at the end, and if you do have any, you can ask them using the question tab on the GoToWebinar software. Thank you. Over to you, Caroline.
Hello, and thank you, Lily. As I said, welcome to the Introduction to OxTS and Inertial Navigation Systems. Excuse me 1 minute. As Lily said, the webinar is being recorded. It will last approximately 30 minutes, so the presentation material will. There'll be time for questions at the end, so please ask any questions you have using the questions box as we go. Let's start by having a look at what is an RT or any of the OxTS products. An RT is an advanced precision inertial and GNSS navigation system. It measures motion, position and orientation really accurately, and it uses inertial navigation system technology combined with survey-grade GNSS receivers. It blends the best attributes of inertial navigation and GPS navigation to give an optimum solution, and it gives improved performance over GPS-only ones by providing accurate velocity updates in urban or tree-covered environments. So what's actually in an RT? What do you get in the box? Well, it can be split up into 4 key components: the GNSS card, the IMU block, the CPU board and intermediary electronics, and the output interface. Over the next couple of slides, we're going to have a look at each of these components in a little bit more detail. First of all, the GNSS card. This provides the unit with an external source of data and is the absolute reference point for both time and position. It's also the main factor when determining positional accuracy. The IMU block is the heart of the unit and provides a constant 100 Hz or 250 Hz data stream. The IMU contains the accelerometers and the gyroscopes. The CPU board and intermediary electronics, this is the brains of the unit. It's what runs the OxTS navigation engine, and it's what logs the data. The output interface, this provides the input-output for the system, and there's various different connections for applications. On the front panel, there's a couple of LEDs, so you can see how your system is operating just by glancing at it. We're now going to have a look at GNSS itself and how it actually works. So, first of all, a bit of terminology. GNSS is the overriding term for Global Navigation Satellite System. It comprises of 4 systems: GPS, GLONASS, Beidou, and Galileo. GPS is the backbone and the US system, and the ones shown in red are the ones currently supported by OxTS. Differential corrections, they're a method of improving positional accuracy. SBAS, satellite-based augmentation system, and RTK, real-time kinematic differential corrections. So how does GNSS actually work? Well, you can split it up into 3 different segments. First of all, we have the space segment. This is satellites in orbit, which transmit signals to the Earth. Each satellite transmits a piece of information. GPS, a pseudo-random number, and this is the unique satellite ID signal. It also transmits almanac and amphoris data. This is the information on satellite locations. Down on the ground, we have a control segment. This is a ground-based network of control stations, and it monitors for clock corrections and orbital model updates. And then we have the user segment. That's us, that's the RT. That's equipment that processes the received signals and calculates velocity and position. So what are the key characteristics of GPS and GLONASS constellations? Well, GPS is the US-based system and GLONASS is a Russian-based one. GPS is the backbone of most GNSS-based systems, and we use GLONASS to supplement GPS for better performance. Now, here are the key differences. GPS, each satellite has its own code. All satellites use the same frequency. With GLONASS, all satellites use the same code. Each satellite has its own frequency. This means that for GPS, you have 2 discrete carrier frequencies, one for L1 and one for L2. For GLONASS, you have 2 ranges of carrier frequencies, a range for L1 and a range for L2. So I'm just going to say that again. The key differences: GPS, each satellite has its own code. All satellites use the same frequency. GLONASS, all satellites use the same code. Each satellite has its own frequency. That's all well and good, but how does it actually work? Well, it works on the principle of speed equals distance over time. We need to know the distance. We already know the speed signals travel at, because that's the speed of light, and we can measure the time taken for the signal to travel from the satellite to the receiver. How do we measure time? Well, we synchronize the code from the satellite to the receiver. So in order to make that calculation, the receiver must be able to tell precisely when the signal was transmitted and when it was received. So when the satellite signals are transmitted, it's a transmitted code and it's sent with a timestamp. And when it's matched to that in the receiver, the distance in time is known. We need to measure time really, really accurately. If I told you that measuring time to a millionth of a second, you'd say that's pretty accurate, but that could potentially result in up to a 300-meter error. So how do we actually use that information? Well, GNSS computes position by using something called trilateration. But to understand that, let's first of all look at it in 2D. And we're going to ask a series of questions. So first of all, where am I? And the first piece of information you're given is that you're 90 kilometers from London. So you're able to plot a perimeter potential location of a radius of 90 kilometers. Second piece of information you're given is you're also 75 kilometers from Birmingham. You now plot a circle of radius 75 kilometers, and this narrows you down to 2 potential locations. Satellite 3 gives you another piece of information. You're also 140 kilometers from Cardiff. Plotting a third circle of radius 140 kilometers, and you narrow down to a single possible location. Every time you add a piece of information in, your positional certainty can increase. So let's have a look at this in 3D now. Satellite 1 gives you a potential sphere of locations. Adding in satellite 2, and you're now down to a circle or a 2D plane. Satellite 3 narrows you down to 2 possible locations. In order to get satellite fix, you need 4 satellites. So what are the error sources associated with GNSS? Well, first of all, let's look at how accurate GNSS actually is. We tend to quote GPS accuracy in the region of 1.5 to 6 meters CEP. And CEP refers to the radius of a circle in which 50% of the values occur. So if we quote a CEP of 5 meters, then 50% of the points lie within that circle of a 5-meter radius. So what are the sources of GPS errors? Well, it can be split up into 2 different areas. One dealt with by the receiver algorithms, and one dealt with by physical setup. The satellite orbit errors, clock biases, and so on are dealt with by the receiver algorithms. And things that we can affect are physical setup and atmospheric conditions. So how do we account for atmospheric variations? Since satellite signals don't travel at a constant speed due to atmospheric conditions, we can account for this using differential corrections. The type of differential corrections that you use will depend on the environment that you're operating in, so proving ground versus open road, where you're located in the world, and what level of accuracy you require, and also your budget. So starting from the lowest end, you can have SBAS. So there's various free services such as WAS and EGNOS, or you can have a paid correction service which can get you down to 1 centimeter, such as TerraStar. If you're on a proving ground, you can have a local base station. So the OxTS products would be the RT base S or the GPS base. If you're down on the open road, you can use get corrections from a correction provider using something like NTRIP. And again, you can get down to as good as 1 centimeter accuracy. Options for delivering SBAS corrections, well, the pros and cons. Well, there's no subscription charge. It gives you better accuracy than SPS. Cons, it's not available worldwide, and SBAS is only compatible with GPS, not GLONASS. The most common solution for use in a proving ground is the use of a local base station. The base station is set at a known location, or it's left to average its position over time. The base station then compares the data that is received from the satellites, and the correction in each satellite's measurement is transmitted using radio modems. The nearby GNSS receivers also have radio modems to listen for these corrections. It's important to remember with a local base station that differential corrections change the way in which a GNSS receiver works. It's now effectively measuring its position relative to the base station and not its absolute position on Earth. This means that if the base station antenna is moved, the remote receivers also move. When you're powering the base station down, you must always put the antenna back in the same location, and you must restore the position. NTRIP corrections are transmitted over a mobile network such as GSM. To get NTRIP corrections, you're going to need an internet connection, and you might also require a subscription to a correction provider. For the shortcomings of GNSS, if you don't have view of the sky, you won't see any satellites, which means you don't get any position update. So this illustrates here. So you can see here there's an output, GNSS output here from an RT, and you can see the unit goes into a tunnel at the bottom of the screen. Once it's going through the tunnel, there's no positional update. Focusing on this top area here where the tunnel exits, it takes time to reacquire signal, which it does before going under a bridge. Again, loses signal, takes time to reacquire before outputting consistently again. It's also very sensitive to the obstructions nearby. So on the left, you've got good open sky conditions. And you can see good correlation between the GPS trace and the RT trace. As we move over the screen to the right, we're seeing some obstructions to frequent obstructions, including a complete sky obstruction with a bridge. And you can see there's more noise on the GPS trace versus the RT trace. This can result in a positional error. So here is an output from the RT in red and the GPS trace in blue. And that was taken in an urban canyon. And you can see there's much more noise on the GPS trace than there is the RT trace. Why is that? And that's due to something called multipath. The signal is received multiple times because it bounces off buildings, and it can cause position and timing and thus positional errors. We can also get multipath errors due to our physical installation in the vehicle. Most of the OxTS antennas require a ground plane. They need to be mounted on a magnetic surface to filter out signals coming from below the antenna. You might ask the question, does adding an additional constellation such a GLONASS improve positional accuracy? Well, let's look at two scenarios to answer that question. Scenario 1, you're in an open sky proving ground. You're tracking 8 satellites reliably, and you're reliably receiving carrier phase corrections, getting down to centimetre level precision. You add GLONASS in. You're now tracking 14 satellites reliably. Scenario 2, you're in a built-up urban environment. You're tracking 4 to 6 satellites intermittently, and you're only occasionally receiving carrier phase corrections. You add GLONASS constellation in. You're now tracking 6 to 9 satellites intermittently. If you're tracking and using less than 6 satellites, you're not able to hold stable RTK. In order to hold stable RTK, you need to be tracking a minimum of 6 satellites. The benefits of combining constellations. You get increased satellite observations and improved ability to work in partial sky coverage. You get increased spatial distribution of satellites and quicker resolution to 1 centimetre accuracy, and improved RTK in difficult conditions. Spatial distribution of satellites. If you've got a high dilution of precision, such as in an urban canyon where you've got lots of buildings on the edge, you get a very tight clustering of satellites, which could lead to a relatively high positional uncertainty. If you're out on a proving ground, the satellites in view are well spaced, and this means that you've got a much lower level of uncertainty. What are the pros and cons of GNSS? Well, it's next to reference point and it's got worldwide availability, and it's continually being improved. However, it's sensitive to the obstructions in your operating environment, and it's dependent to the satellites in view. Moving on now to the IMU core and how it works. What is an IMU and how does it get the information? Well, an IMU is an inertial measurement unit, and it measures accelerations and angular rates. It measures these using accelerometers and gyroscopes. It measures the linear acceleration in an axis and the angular rate around an axis. And from this, we can get our velocity and orientation. The accelerometers will measure your acceleration in your X, Y, and Z directions. And from this, we can integrate it to give the velocity. Integrate again to give the distance travelled. Our accelerometers will also be able to tell us what direction gravity is acting in. The gyroscopes will be able to tell how fast it is rotating around an axis. From this, we can get our angular accelerations in each axis by taking the differential of our angular rates. By taking the integral of our angular rates, we're able to get our orientation, or our pitch, roll, and yaw. An IMU enables us to use something called dead reckoning. So by starting from a known location, an IMU can tell how fast and how far we're travelling and in which direction. And this means that position can be estimated without GNSS updates. An IMU will always have some form of error, so positional error can build up over time. So with dead reckoning, you start at a known location with known heading. Accelerometers will be able to measure how fast and how far you have travelled. The gyros will measure your change in direction. This means we can estimate our position here. How does error relate to this? Well, there's an error margin in your velocity and distance measurements. There's also an error in your orientation. And this means that your area of uncertainty increases over time. An IMU also lacks a reference point. We're now going to have a look at how an INS actually works. Well, the goal of an INS is to eliminate the two shortcomings of IMU and GNSS technology alone. So the INS uses GPS updates to correct for positional drifts. Update rates are 2 Hz for GNSS and 100 Hz for IMU. And this means that for half a second, the INS uses dead reckoning to estimate position. This means that when GPS signal is lost, the position is still computed, but with an ever-increasing error. We have a Kalman filter to help with this, but it's important to remember that the Kalman filter does not filter the data, instead it filters the errors. The output from sensors are directly after the error corrections have been applied. The role of the Kalman filter is to make the difference between the GPS and inertial measurements as small as possible. To do this, we take the error signal, which we call innovations, and we use this error to figure out what parameters in the strap-down navigator are incorrect. So we use the strap-down navigator to process the measurements further. It applies the corrections from the Kalman filter to the angular rate inputs. It also corrects for earth rotation and transport rates. It then integrates the angular rates to give the heading, pitch, and roll. The accelerations are corrected for bias and rotated using the heading, pitch, and roll. Gravity and Coriolis accelerations are removed. Then the accelerations are integrated to give velocity and integrated again to give position. All the integrations have the corrections applied by the Kalman filter, so we've corrected for any drift that occurs. The Kalman filter manages 26 different states. It measures position, velocity, and orientation in 3 axes. Your gyro bias and scale factors in 3 axes. Your accelerometer bias, GPS antenna positions, GPS antenna orientation, vehicle mount angles, and your wheel speed scale factor if you're using it. But what do we get out of the RT or the OxTS products? Well, it depends what sort of output interface you use. With the RT3000s, we can output over RS-232, Ethernet, or CAN. Over the CAN connection, you'll get CAN messages. Over RS-232, we'll get ENCOM data or NMEA, and over Ethernet, we'll output ENCOM data. ENCOM is a proprietary format and it's specific to the RT. We can also provide C code drivers to help you decode if you want to decode the messages yourself. Otherwise, this is done in the OxTS software, and it can be decoded to give other measurements such as distance, slip angle, lateral drift, or track angle. What does it measure? Well, we've only got a couple of fundamental measurements from which everything else is derived. So in 3-axis, we measure position, orientation, acceleration, angular rates, and velocity. And from this, we can derive all other measurements. The OxTS products can output into 3 different frames. We can output in what's called the navigation frame, which is also known as the northeast down frame, the level frame, or forward lateral down, and that can be aligned with horizon, or the vehicle frame, and this is where the rotations have been applied so the vehicle, so the RT is orthogonal with the vehicle. We can also output our angular rates in the vehicle frame or the level frame. I mentioned at the start that on CPU board and intermediary electronics, the data was logged. Every time an OxTS product gets satellite signal, we log something called RD, an RD file. And this RD file contains things like your configuration, your GPS data, and your IMU data, and details of any feature codes. We can then process this data using the OxTS software, and we can process it using different methods. We can do simulated processing or combined processing. We can also process in GXIX mode. We can also add additional RINEX corrections if necessary. Because we log raw data, we can change the configuration. We can make corrections or alterations. It's important to remember that the GPS data and the IMU data is fixed. If there's some errors with that, we can't do anything with it. That's done. But we can make changes to the configuration. So if you realize you made an error, or if you want to see the effective output displacement or something like that. So we can make some changes in that in post-process and create a reconfigured or revised ENCOM file. Well, thank you very much. That's the end of the presentation. We've got some time for questions if anybody has any.
Hi there, Caroline. So we don't have any questions in yet. So we'll just wait for a little bit. So if anyone does have any questions, this is your time to ask them. Just another thing to add, we are running some other webinars on some different topics. If you want to check them out, the link is on the screen now, just OxTS/resource hub. And we also have a support site with lots of articles about different setups and situations that may also be helpful. So the first question we've had in, what's the difference between DGPS and RTK?
DGPS, differential GPS, that'd be a differential corrections. RTK is the position mode, so that'll be when you're down to the highest level of 1 centimeter accuracy. Whereas differential corrections can get you down to different levels of accuracy, depending on what type of corrections you're using. So, for example, you could be using SBAS, which will only get you down to 20 centimeters accurate, or you could be using enteric corrections from a source that's a very long way away, which might only get you down to 20 centimeters. RTK is a subset of that, would be when you're down to centimeter level precision. or that sort of level.
Okay, thank you, Caroline. Does anyone else have any other questions? If not, we'll just end the webinar a little bit early.
Thank you all very much for attending. And as Lily said, thank you, and check out some of the other webinars. The links on the screen. Thank you all.
Yeah, thank you.